Hi, everybody. Welcome to CPB's seminar. So today we have Mary Fisher, who started here just in January. She started out getting her bachelor's at Cornell, then started at a master's at the University of Washington, where she was in the School of Aquatic and Fisheries Sciences, and doing a lot of ecological genetics relevant work, and then did a pivot to starting to think about social ecological systems and more multidisciplinary work. And so changed schools, but still at University of Washington, into the School of Environmental and Forest Science, working with Phil Levin for her PhD, where, as you'll be hearing about, she did some amazing work on adaptation to climate change in these social ecological or coupled human natural systems. And in particular, you know, this project on the Dungeness crab, where Mary, as a PhD student, was playing a leadership role in an 8-institution project that was deeply community engaged. And she is continuing that multidisciplinary vein as a postdoc co-advised by myself, Tyler Scott, and Mike Springborn. So bringing in both the natural sciences and the social sciences, bringing these types of things that you'll be hearing about to the lens of kelp restoration here in California. So we are absolutely delighted to be having Mary here for the next 2-ish years, and excited to be hearing about her postdoc work. Or sorry, her PhD work.
I think I can skip the first couple slides now. So I am going to be talking about one part of my dissertation work today. That's going to be like the main part of the talk, and it'll be focusing on social ecological network analysis for the Dungeness crab fishery. And then I think it's going to be a pretty fast talk. And so towards the end, I'm going to list out a few additional applications of network analysis methods to fisheries from work that has been led by other folks, but provides kind of a more comprehensive outlook of what this type of method can do in fishery science, and then kind of identify a couple of future directions that will get some discussion going after the talk. Now, the reason that my dissertation work and most of this talk today is going to focus on Dungeness crab is because it's the most valuable single species fisheries on the US West Coast. So it supports over 1/4 of all California commercial fishing vessels, which is a huge amount. And those vessels span from small-scale family operations to large vessels over 60 feet in length that transit the entire coastline. And while many crabbers are going to be participating in a range of different fisheries, a good crab season is a really crucial source of revenue, as is demonstrated by this quote here by a Crescent City crab fisherman. And something that's going to be important a little bit later in the talk is that the revenue itself is highly seasonal. So Dungeness crab is one of the last derby-style fisheries on the West Coast, which means that most of the catch is landed within the first 6 to 8 weeks after the fishery opens. And that's captured here by this graph of cumulative landings by week of the season on the x-axis. And I want you to ignore the colors and just note that the bar graphs hit their maximum very, very close to the beginning of the season within those first 6 to 8 weeks. And the revenue from these landings isn't just important to crabbers. So a good Dungeness crab season for many coastal communities supports seafood processors, markets, restaurants, and other local businesses. And as someone from Crescent City put it, if there is a Dungeness crab fishery closure in many coastal towns, it'll affect anybody with a local and small business. So the crab fishery is considered sustainable, which means that closures like that weren't much of an issue until around 2015. And some of you are probably sick of hearing about the 2014 Pacific marine heat wave called the blob, but here it is again. It formed in the Northeast Pacific Ocean, and this map is just showing how the heat waves, low nutrient, high sea surface temperature waters in orange and red kind of moved in towards the coast in April through June 2015, combined with high nutrient waters from the spring upwelling, and caused a coastwide harmful algal bloom, or HAB, of Pseudonychia. And you can kind of see the formation of the bloom between these two maps of chlorophyll A concentrations from March to May 2015, where that red is coming up all along the West Coast in May. The bloom produced record-breaking toxic levels of domoic acid that accumulated in shellfish, including Dungeness crab, And so to protect consumers, a lot of shellfish industries were shut down across the West Coast, and that included the Dungeness crab fishery. The toxin levels from the bloom were highest in California. And so this is where the start of the commercial Dungeness crab fishery was delayed the longest. And these delays were implemented using staggered area closures along the coast, with each area opening up as soon as possible to try to maximize fishing opportunity. And despite this structure, the crab fishery did end up losing 58 to 78% of their entire season in 2016 and up to 21% of the entire 2017 crab season. And I just wanted to emphasize how much of the season that really is for the 2016 fishery. So each of the boxes on this plot are going to show 1 week of when the fishery is normally open. All of the red boxes are the weeks that the fishery was closed in 2016, and then green is when it reopened here. And the other thing this graph kind of nicely shows is how the closures were the longest in Northern California, above that Sonoma-Mendocino County line for Crescent City, Eureka, and Fort Bragg. The economic fallout of these closures was enough for the California season to be declared a federal fishery disaster. And we also know that smaller scale owners and smaller owner operators were hit particularly hard, so that even after the fishery reopened, small vessels actually brought in a lower proportion of landings and revenue than they would have in a normal season. And eventually, Congress appropriated over $25 million in fishery disaster relief funds because of this one event. So for my work, we wanted to first dig into some of those uneven impacts between large and small scale operators by asking whether they might correspond to differences in how people responded to the closures. And then we had this hypothesis that because the crab fishery is so important to port communities, and this was such an extreme closure, we wanted to see if we could capture significant changes to patterns of resource use at the port level using social ecological networks. And by doing so, we could then apply some network theory to try to understand what the potential implications were for future climate impacts based off of the changes we observed in 2016. To answer these questions, we drew on over 285,000 unique fishery landings records from 30 different ports of landing along the California coast. And this captured the fishing activity of all registered commercial vessels at these ports between 2008 and 2018. So capturing before, during, and after the 2016 closures. And we came into the research knowing there was that difference in the duration of area closures between Northern and Central California. So we aggregated landings according to 7 port communities that were grouped into a northern and a central region, as I've got here on this graph. And then to answer our first question about how crabbers responded to the harmful algal bloom, we considered responses by vessel size class because we knew that's how the economic impacts were broken up. And so we grouped landings according to larger vessels, which would be over 40 feet in length, and smaller vessels that are under 40 feet in length. To answer our second and third questions about the social ecological networks, we use the fishery landings data to build these multi-level networks. And this particular method is kind of the core of the talk today. Representing fisheries as a social ecological network involves both a social network where the nodes are usually human actors or fishers linked by information or trust, and an ecological network where the nodes are species or species assemblages that are linked in a food web. And then harvest is represented by these social ecological links or ties. And before I really dive into network terms here, has everyone kind of worked or knows of network methods? Can I just get a show of hands? People who, okay. Okay, so I'll just quickly clarify. I'm gonna interchangeably use the word edge, link, and tie because I can't stop myself. And that's basically just any connection between 2 nodes in the network. And then the nodes are the fishing vessel icons or the species icons, just to make sure we've got that clear before I really get into it. Okay, so we have our multi-level social ecological network. And then from here, we can actually add weights to the social ecological ties using our revenue data. And that gives us a fully articulated weighted network. But having the information and granular data to construct every single edge in this network at all levels is really time and resource intensive, especially if you want to work across multiple communities across the entire coast. And since the focus of our research was really on patterns of harvest or the social-ecological links, we worked with a partially articulated network that didn't look at exclusively social or exclusively ecological types. And then we took this network and projected it into something called a unipartite network, which we call a fisheries participation network, in which the nodes are the fished species or species assemblages, and they're connected by vessels that are participating in both of those fisheries. The edges in our participation networks are weighted to be proportional both to the total revenue that a vessel is making from those two fisheries and the evenness with which that revenue is distributed. And so this equation that I've got up here to describe the weighted edges just sums a vessel level index across all vessels that fish in both fisheries I and J, which are crab and salmon up here. And if we look at this calculation just for one vessel K at time T, as the proportion of revenue from fishery I versus fishery J approaches 50-50, we'll see that the edge weight is going to increase. And then as the contribution of both fisheries I and J to the total vessel revenue increases, so does the edge. And again, that just creates this effect where edge weight is proportional to the total revenue as well as the evenness with which that revenue is produced. Okay, we constructed these networks for each of those 7 port communities. And for each port community, we had 2 networks per fishing year to represent an early season and a late season. And the way we broke this up was that the early season was the weeks the fishery was closed in 2016. So that's predominantly winter to spring fishing activity. And then the late season was the weeks where the fishery had reopened in 2016. So that would be late spring to summer fishing activity. And we modeled the changes in network structure through time to determine what significant changes were associated with those 2016 closures. Specifically, we looked at network structure according to centralization, modularity, and edge density, which are 3 network metrics that are theoretically related to the vulnerability of a system to perturbation. So sensitivity here just means the magnitude of change in a network caused by a perturbation. And then for fisheries participation networks, we're looking at adaptive capacity in terms of the flexibility to switch between revenue sources in a network. And I have equations for these at the end if anyone's interested, but I'm just going to go through a quick graphical summary right now. So centralization is just the degree to which the network is centralized around a single fisheries, and it's directly related to sensitivity because higher centralization around a particular node makes the network as a whole more sensitive to the disturbance of that node. Modularity is the degree to which the network consists of self-contained substructures, and it's inversely related to sensitivity because the more modular networks tend to constrain a perturbation to the substructure where it's occurring. And then finally, we have edge density, which is the proportion of total possible edges that are actually present in the network. And in participation networks, a greater edge density is going to represent more flexibility. Okay, so we use these network metrics as response variables in a set of nested generalized linear models in order to attribute changes in the metrics to the 2016 HAB closures. And we captured the effect of the closures with this closure duration variable that I've listed on the top up here, where the 2016 closures were the only ones in our study that were represented by this high duration closure effect. We then had a medium duration closure for other years and a no closure for the remaining years of the study. We've also included the crab fishing year, the region as North and Central California, the port community, and network size as our predictor variables. Okay, so let's start the results with our first question. How did this extreme event reveal uneven capacity to respond? The landings data that we looked at let us track 3 different possible response strategies at the vessel level. And we found that during the closures, 71% of all vessels, and that's large and small vessels, which had fished Dungeness crab in prior seasons, stopped fishing entirely for any species during the Dungeness crab fishery closures. There were some other vessels that were able to adapt in place by fishing for other fisheries during the closures, and that's at the bottom of this very nice graphic from NOAA. The specific fishery that people relied on varied by vessel size and location, but we did generally notice that there were a greater range of alternative fisheries at ports in Central California compared to Northern California. And then finally, some of the vessels which had traditionally landed catch up in Northern California took advantage of that staggered opening structure to move down into Central California and catch crab, where the crab fishery opened up earlier. And these were almost exclusively larger vessels, greater than 40 feet in length. We didn't see quite as many changes in fishery participation after the closures ended. So this is after the crab season has opened in 2016. There were a handful of small vessels that never returned to fishing in California during the following year. So those vessels regionally dropped out of fisheries. And then there are some vessels who ended up choosing to fish for Dungeness crab at the expense of other fisheries that they normally would have participated in at this time of year. For both large and small vessels, that tended to be salmon fisheries that they kind of gave up the chance to participate in, although it's worth noting that at the same year had some fishery disasters in salmon as well, so that might have factored into the decision to catch crab instead. So now we have these vessel level responses, and we wanted to tie them to changes in port level social ecological networks. And just as a reminder, those port level networks are all fishing vessels at the port, not just crabbers. So according to our generalized linear models, edge density and centralization were significantly affected by those 2016 hab closures, and they were significantly differently affected between Northern and Central California. So in Northern California, we saw lower edge densities and lower centralization. Even though we modeled these structures across 10 years and 4 different port communities, I think that these kind of network images for the Eureka port communities demonstrate these changes pretty well. You'll notice that there's no 2016, or there's no Dungeness crab in the 2016 network because the fishery was closed at that point. So the decreased edge density that you can see in these Eureka networks was associated with the fact that the majority of the vessels that continued to fish in Northern California during the crab closures concentrated their participation in a single alternative fishery instead of multiple fisheries. And then we also think that if vessels that stopped fishing or vessels that moved would have participated in 2 fisheries at the same time, that could have contributed to that decline in edge density. In contrast, in Central California, we actually saw an increase in edge density during the 2016 closures compared to previous and subsequent years, and a similar decline in centralization without Dungeness crab in the network. And that's pretty well demonstrated for these 2 networks from Monterey, California in 2015, the year prior to the closures, and in 2016, the year of the closures. So this could be due to the fact that vessels that remained active in Central California when Dungeness crab was closed actually increased the number of non-crab fisheries that they would have otherwise participated in. So the proportion of active Dungeness crab vessels participating in 2 or more fisheries doubled between 2015 and 2016. But at the same time, a lower percent of all of the vessels at a port in Central California participate in Dungeness crab. So there's also a chance that these changes are more likely to come from dynamics external to the crab fishery. We did not end up observing any significant effects of the 2016 closures in the late season participation network. So this is late spring into summer fishing activity when the fishery had reopened in 2016. We did see some minor increases in centralization, but these weren't significant, especially when centralization included those edge weights I talked about before. And you can kind of see that in these networks from Eureka between 2015 and 2016. Okay, so what are the implications for future climate impacts to port communities as a whole? As we saw on the previous slide, there were minimal structural changes after the crab fishery reopened. So at the port level, patterns of fishery participation were relatively resilient to these harmful algal bloom closures. But we can also ask in a future with more frequent marine heat waves and more intense harmful algal blooms, what if Dungeness crab vessel operators were to more permanently adopt some of those alternative fishing practices that we saw during the 2016 closures? And so let's just go back to those early season networks that represent winter to spring fishing activity. I'm going to summarize what I said before in this table on the bottom left. So based off of our generalized linear models, we know that sensitivity related to centralization decreased in Northern California, whereas adaptive capacity also decreased related to edge density. And that in Central California, we saw a decrease in centralization and an increase in edge density. Translating this using network theory, decreases in centralization are generally good for lower sensitivity, but that decrease in edge density in Northern California is not a good sign for adaptive capacity. So this is suggesting that Northern California fishing communities could become more vulnerable to secondary social or ecological shocks during a period where Dungeness crab fisheries are closed. And there's a kind of a technical term for this. It's a type of social trap called a gilded trap that was first described in the Maine lobster fishery. Basically, there's kind of strong social drivers that make a fishery like crab very valuable, and it makes it a rational decision to kind of concentrate effort in that fishery on the social side of things. But because of ecological factors, this investment might lock people into a fishery that puts them at greater risk of negative impacts in the long term. So just to sum up all of those different threads of thought here, I just talked about how a lower capacity to adapt to secondary shocks in Northern California creates what might be called a seasonal gilded trap in the fishery. And this was a conclusion that we drew based off of significant and regional specific changes in network centralization and edge density as a result of the 2016 closures. And those significant changes were related to some of the vessel level responses that we observed in the fishery landings data, which varied by region and also between small and large vessels in some cases. Okay, I think I have plenty of time to go into the next section. So I just want to move on from a kind of network and systems level analysis and talk about how social ecological networks can also be used to track the changing roles of individual fisheries in West Coast fisheries over time. And so we're moving from this place where we already knew how important Dungeness crab was, and we focused on network metrics, to a place where we want to investigate the importance of a specific fishery and what that might mean using node level metrics. And considering this kind of level of importance or connectedness of an individual fishery gets at the identification of something called insurance fisheries. So these are fisheries that might absorb displaced fishing effort and mitigate risk. And another way of looking at this is that those same fisheries might facilitate a lot of indirect cross-fishery consequences of regulatory changes that affect access or fishing effort. And so I'm just going to give a quick example of each of these themes from research that I was marginally involved in, but which were led by other folks. So both of the examples that I'm going to talk about use a metric of node strength, which quantifies how connected a single node is to other nodes in the networks. And I've leaned on this graphical summary again, just to show that a node with high strength would be that central node in a star network on the left-hand side, and then low strength would be a peripheral node. So the first example around insurance fisheries is part of a paper led by Tim Frawley on the albacore fishery, which is one of the last open access fisheries on the West Coast. And Tim used node strength to demonstrate how the albacore fishery, which is this blue line on the graph right here, increases over time for small vessels in the Pacific Northwest. And that is showing how the albacore fishery is becoming an increasingly important component of a diverse portfolio for small and medium-sized fishing vessels on the West Coast. And Tim ended up combining this network analysis with some other economic indices to document the role of the fishery as an insurance policy for periods of time when other fisheries in the portfolio were closed. The second example is work led by Jamil Sempori for the California Current Ecosystem Status Report. And this was focused around the rebuilding of the quillback rockfish stock in Oregon and California, which is part of the species complex that's represented by the teal circled node in this participation network for Fort Bragg. In 2020, a stock assessment found that the quillback rockfish stock was below the minimum stock size threshold, and that initiates a bunch of regulatory and scientific actions. And so Jamil used node strength calculated from 2020 fisheries participation networks to identify where regulatory changes associated with this quillback rockfish rebuilding might lead to high spillover of effort into other fisheries. So on this graph right here, that's going to be any of these ports that are kind of up on the top part of the left or y-axis, like Astoria, Fort Bragg, Eureka, and Morro Bay. But Jamil also took that node strength and graphed it against revenue and showed that while fishery revenue is a reasonable proxy for these more complicated network-based metrics, to show how strongly connected the quillback rockfish species complex is to other fisheries. There were also some cases where ports fell above this line of best fit, so that would be like Brookings over here, which indicates that these port communities might be subject to more spillover or leakage than would be suggested using just a revenue-based index. So that network metric is adding some value here. And then other ports like San Francisco are falling below the line, so they might be less likely to experience large amounts of spillover and leakage from these regulatory changes, despite what the revenue might suggest. Okay, and so I think in terms of future directions, having additional case studies like the one I just talked about that kind of demonstrate the unique contributions of network analysis compared to more traditional revenue-based or economic metrics is, I think, will be a major contribution to the use of this and institutionalization of this type of analysis for fisheries management and just kind of general understanding of coupled human natural systems. And I think another major thing that needs to be on the to-do list is also kind of moving past descriptive analyses like the one I just spent a bunch of time talking about, to try to more empirically link certain network structures to sensitivity or adaptive capacity that you might be able to do by looking at revenue variability through time or variability in fishery participation through time. And that's kind of similar to what's been done on fisheries portfolio diversification in Alaska, or if you're a social network person on like triadic closure. I will say that the paper came out like within the past 2 weeks from Tim Frawley, who actually started working on doing this, where they took economic outcomes and directly compared them to what would be predicted based off network metrics. So highly suggest anybody who's interested in that, check out that new paper, which I was not involved in. Okay, I guess all I have left to do is thank my co-authors from the Northwest Fisheries Science Center, UW, and Oregon State University. I also want to just say that a lot of this quantitative work wouldn't have been possible without the intense qualitative survey and interview effort that some folks did at the Northwest Center and the University of Washington. And then data was provided by PacFin and the Northern Office of Law Enforcement and the California Department of Fish and Wildlife. Plenty of time for questions, I think.